Record on this computer. We're going to review Chapter 5 in your textbook, and for Exam 4. So that'll be on thermochemistry in a second. Let's see. Were you guys here for last week's lecture? Okay, good. So we just need to cover some topics that you might feel uncomfortable with since you had to leave early. Okay, for sure. And then where do we start? Let's see. We start where you want to start. How about that? And then we'll go from there. Okay. One of these that works. Well, what shall we do first? Take it from the top, see where we go?
Yeah.
Okay. So, question number 1 says, a gas absorbs 0 joules of heat, but then performs 30.7 joules of work. So what's the change in internal energy? Okay, so we need, the question is internal energy. So we need the expression for internal energy, which is the sum, oops, not a G, it's a Q, which is the sum of heat transfer and work. So the problem says that no heat was transferred, right? So this is 0. Right? And the work that was done by the gas on its surroundings. So that means if we have the system here and the surroundings here, then the work is being done like that, right? It's doing work on the surroundings, so that means it's a negative value. The magnitude of the value is 30.7 joules. But since it's doing work on its surroundings, that value is negative. Okay? So the overall then would be negative 30.7 joules. Okay? That one's already starting to get weak on me. Hope it shows up okay. Yeah. Camera's better than I thought it was. Okay. Brace is good too. Let's see about the black ones. They usually want to stick around. Don't wipe off too easy. Okay, what about kinetic energy. That's always a fun problem. What's the kinetic energy of a 1.56 kilogram object? So mass is equal to 1.56 kilograms. And it's moving at 94 kilometers per hour. So the velocity is 94 kilometers per hour. Okay, how do we calculate kinetic energy? With that formula. Okay. The trick is to use the proper units. Right? Because if we're going to express energy in joules, these have to be in standard units. So the mass has to be in kilograms. That's good. It's already in kilograms. Velocity has to be in meters per second. Okay. So that's the one that we need to convert. So we'll take this one. And remember, when you have 2 units to deal with, do them one at a time. So we got to convert kilometers into meters. Meters. So how many meters in a kilometer? And the third, 1,000 meters in a kilometer. Okay, so that cancels this one there, leaves us with meters. So we're halfway there. Now, hours. Okay, if you don't know how many seconds are in an hour, you need to chain your conversions. Right. And since hours is in the denominator, it needs to be in the numerator here to get rid of hours. So I know minutes, like 60 minutes in an hour. And then we want to get rid of minutes, so it goes up here and make it seconds. So 60 seconds in a minute. Oh, 3,600 seconds in an hour for future reference. And then we'll do the conversion. So we need 94 times 1,000 divided by 60, and then divided by 60 again. So that's 26.1. Yeah, pretty significant figures. Meters per second. Now you can plug it into your formula. So we have 1/2 mass, which is 1.56 kilograms, and then 26.1 meters per second. And don't forget the square. Okay? So we can take 26.1 and square it. Let's see, I'm using a different calculator. There it is. And then 1.56 times that and divide by 2. So I get 531. If we take just these units, we're going to have kilogram meters squared per second squared, which is joules. Okay? All right, let's see. Okay. So 3 says, which of the following statements correctly describes the signs of Q and W for the following exothermic process? Not behaving. This one. Let's see. That works. Yeah, black needs to stick around. Gotta stay away from black. Okay, so we're looking for the signs of Q and W. An exothermic process. Okay, exothermic, that's the easy part. The sign on Q is going to be negative. Okay. The one that's going to take some thought is W. If we're at standard pressure, and a temperature of 370 K, which really doesn't matter. That's what we call fluff or blue smoke. You don't even need to know that to answer this question. You're going from, here's the meat of the problem. You're going from gas to liquid. I guess this does matter because we're holding the pressure and the temperature constant. You know, that's important. And so what is the W going to be? You have to decide, is the system doing work on its surroundings or the surroundings doing work on the system? Okay. So recall, what we're dealing with here is a gas that's condensing to a liquid, and you're under constant pressure. So what happens if you're under constant pressure? You condense. If the vessel is rigid and you condense, then you create a vacuum. I can remember one thing my father used to love to do was wow his students. He taught 8th grade earth science. And he would get one of these paint cans or turpentine cans and clean it out and fill it with just a little bit of water in the bottom. And then he heat it up, which would expel all the air and fill it with steam. And then he would cap it and pull it off the heat and just let it sit there. And as it cooled down, the water would condense into a liquid again. And the can would just go and just crumple like that. Because the pressure inside would be drawing a vacuum. You'd be losing the gas pressure and changing it to a liquid. So you have all this external pressure that's unbalanced and it would crush the can. So, but that's, and that's with constant pressure because the pressure didn't change on the outside. So what's happening? Well, if we keep the pressure constant, right? So we have a force here, and P equals 1 atmosphere. Then as the water vapor condenses into a liquid, we're drawing a vacuum here, and the volume is decreasing, right? So remember, the expression work equals minus pressure change in volume. So pressure is constant. The volume is doing what? The volume is decreasing. So that means it's negative. And a negative times a negative is positive. So this one is going to be positive. You can tell that from the formula, but you can also tell just by looking at what's going on here, right? Because this is the system, and the pressure is applying pressure to the system, and that means that it's doing work on the system. Okay. So either way it works and gives you the correct sign. Okay. Let's see. Are we going to get off the first page?
So what was Q?
Oh, Q was negative, right? Because it's exothermic. Yeah, that was the easy part.
Oh, it says that. There. Okay, yeah.
Yeah. Let's see. And I don't want to do a lot of repetition because we'll run out of time if I do. So let me try to find something unique. Unless you have one that's really bugging you, then we'll jump to that one. 7 is just an application of that formula, W equals minus P delta V. So that shouldn't be a problem.
Let's see, 8's another application of the same principle. What's another thing? Oh, okay. So how about 9? This one looks complicated. A fuel-air mixture is placed in a cylinder fitted with a piston. Okay. So that means it can move and the volume can change. And that means the pressure is going to be constant, which is good. The original volume is 0.31 liters. Then we ignite the mixture, and it produces 935 joules of energy. Okay. To what volume will the gases expand against a constant pressure of 635 millimeters of mercury? If all the energy released is converted to work. So what that means is that energy that's released by the reaction is not leaving the system. It's internal energy and it stays there. So it will be converted into work. Okay, so what we're saying, let's just write down what we know. It's always a good place to start. What do we know? Let's see. We know the initial volume is 0.310 liters. We don't know the final volume because that's the question, right? To what volume will it expand? And we know the constant pressure is going to be 635 millimeters of mercury. Okay. We need a conversion factor. What we're saying is that all of the heat in that reaction is converted into work on the work against that opposing force. We're doing work on the surroundings. So the heat that's produced, it's exothermic heat, which is 935 joules, is being converted into work on the surroundings, right? So the work is a negative 935 joules because we're allowing the gas to expand, okay? Now, what we need to do is, since this is in terms of pressure and we want volume, what we want is negative P delta V. We want this in liters and that in atmospheres, right? So we need to convert this to liter, where is it? I saw it just a second ago. Joules. We need to convert this into liter atmospheres. So it can be equated with this. So the conversion factor, which I think I gave you in class, the conversion factor between liter atmospheres and joules is 1 joule equals 101.3. No, sorry. 1 liter atmosphere is 101.3 joules. That's key right there. Okay. Now, if I forget to put it on the test, just ask me for it. I'll give it to you. So what do we get? Well, as it turns out, this is a minus 9.23 liter atmospheres. That's the equivalent of work that's being done.
Now we can equate this with this. But this has to be converted into, we need a constant pressure in terms of atmospheres. That's millimeters of mercury. So we got to convert this also.
The atmospheres?
Yes, convert it to atmospheres. Yeah, I have this one memorized actually. 760 millimeters of mercury is 1 atmosphere. So we divide 760 into that, and it'll be less than 1. Here it is. 0.836 atmosphere. Okay, so now we have pressure here, and we have work here. We can solve for a change in volume. Right. So the work that's being done on the surroundings is minus 9.23 liters atmospheres. Okay, and that's equal to minus P delta V. So minus P is 0.836 atmospheres. And delta V is always the final minus the initial. Right? Same thing for temperature, final minus the initial. So the final is the one we want to know. And the initial is 0.310. There's your formula, solve the unknown. That should be fine. So this is going to be, let's see, if we take this one and divide it into that one, 9.23. And they're both negative, so we come out with a positive answer. I get 11.04 on that side. And then V sub F minus 0.310 on this side. Then that's a negative over here, so it'd be a positive on this side, but add it to that side. We'll get 11.35. Liters. So the gas expanded from a third of a liter up to 11 1/3 liters. Okay.
The sheet 11.4.
Oh, divide this one into that one.
I don't know what's one. Okay.
Is that showing up? Just barely. Not a good color for this. Okay, anything else? What's this? Look at these over. Okay, does erase all right. All right. So let's see. See what that one is.
Okay. I don't know if that was. Stop me anytime. Take me in a different direction if you want. I'm trying to find something that'll cover several topics at once. What if we actually get to calorimetry, since we're going to be doing that today? We'll take a real simple one first. How about 24?
I should be writing the numbers up here so that the audience can see. How much heat is required to raise the temperature of a 5.75 gram sample of iron from 25 to 79.8 degrees? Okay, this is really simple expression of the calculation of Q when you know the specific heat of your sample. So we're calculating Q, and we need to know what the specific heat of iron is, and it's given us to us, 0.45 joules per gram degree centigrade. That's S. And the mass is already in grams. That's good. 5.75 grams of iron. And then the temperature is final minus initial. So the final temperature is going from 25 to 79.8. So the final temperature is 79.8. The initial temperature is 25. There we go. So grams cancel, temperature cancels, and leaves us with joules. Let's see, 0.45 and 5.75. 79.8 minus 25. So I get 140, 1, 2, 3, 3. Rounded off, 142 joules. Is the heat required to raise the temperature of 5.75 grams of iron from 25 to 79.8 degrees? It takes that many joules to do it. Now, what if this were water? And it was the same mass, same temperature change. Water would be, what is it? 4 point something. It'd be about 10 times as much. I think 4.18, I believe it is. So that means to raise that much water over that temperature span would take about 10 times as much energy as it would for iron, because the heat capacity of water is higher. That's an illustration of the significance of the specific heat of a substance. The higher the specific heat, the more energy is required to raise it a temperature range. Okay. Okay, that's 24.
Now let's see if we can move to something a little more complicated. What's 20? Why did I skip 20? I skipped 25 because it's just I didn't want to bother with it. It was sort of a memory problem. 26 is a calculation.
So eventually, where I'm going to end up is with the lab, and we'll talk about determining calorimeter constant. Okay, that's where I'm headed. We're going to do it in stages. So this problem, 26, show up. Yeah.
we have a 32.5 gram piece of aluminum with a molar heat capacity. And we're heating it to 82.4 degrees. Then we're dropping it in the calorimeter, which contains water, with a specific heat capacity of 4.18 joules per gram degree centigrade, which starts out at 22.3 degrees. So the final temperature of the water is 24.2 degrees, and we're also ignoring, at this stage, we're ignoring the influence of the calorimeter. We're just setting the calorimeter constant idea aside. Okay, this is theoretical. So, what are we given? Okay, the mass of aluminum, is 32.5 grams. And its specific heat is 24.03 joules per mole degree C. So that's the molar heat capacity, specific heat capacity. Okay? That means in order to use this term, we've got to convert this to moles. Because I don't know how to convert this one to grams. I guess I could if I set my mind to it, but I think it's easier to convert this to moles and then use that value. So we'll do that in a second. Let's get everything else up here that we know. Its temperature, the initial temperature of the aluminum before we drop it in the calorimeter is 82.4 degrees. Okay? Now water, the mass of water is equal to, we don't know. That's the question. What's the mass of the water? We do know the initial temperature of the water, which is 22.3 degrees. And we know the final temperature, which is 24.2 degrees C. That's also the final temperature of the aluminum. Because when we drop the aluminum in there, we wait till things just stop changing. They equilibrate, so they're both at the same final temperature. Okay? That's everything we know except for the specific heat capacity of water, 4.18 joules per gram degree C. There we go. Okay, that's everything we know. So, the concept here is that the calorimeter is an isolated system. Everything that happens in there has to add up to zero in terms of heat. Okay? So, that's your starting point. Everything has to add up to zero. Zero equals the change or the heat of the aluminum plus the heat associated with water. Okay? Now, when we write Q here, we're really saying change. Right? We don't write delta Q. Q means change in energy. Because you can't measure absolute energy unless you can compare it to absolute zero. Right? So we have to measure a change between some fixed points. So that's what Q means. Okay, now that we've got that expression, say, what's the Q of aluminum? Well, we need to know the specific heat. We need to know the mass and change in temperature for aluminum. And the same thing for water. Okay? Now that we've got our problem set up, we'll do some
mathematical gymnastics. We need to convert that aluminum to moles because this is in terms of moles, not mass. So we'll take that's many grams of aluminum and convert it to moles, right? So grams on the bottom, moles on the top. Anytime you see that relationship, you know molar mass of aluminum. So let's see, molar mass of aluminum is 26.98. Okay. So we just need to divide that into 32.5. 6.98 is 1.205 mole of aluminum. Okay? So now we go back to this problem. We say, okay, 0 is equal to the molar heat capacity of aluminum, which is 24.03 joules per mole degree C. And then, you know what? That's not right. M stands for mass, right? So what are we going to say for moles? I guess we just have to write it in. Moles of aluminum, right? It would have been right if this were in terms of specific heat capacity, but it's molar heat capacity. So we have to have moles of aluminum.
You can just interchange them like that with that formula?
Yeah, it depends on what the constant is. Right? The units on this determine what these are.
Oh, right, okay.
If that's in terms of moles, this has to be moles to cancel out. So we've got that, and 1.205 moles. Right. Okay, so that cancels this one and that one. Now we need change in temperature. So final temperature, 24.2 minus initial temperature, 82.4. Okay, it's important to do final minus initial because then that establishes the correct sign on your value. If you do it the other way, then you're going to end up with a positive number here and a wrong answer. Okay, now for the water part. So 4.18 joules per gram degree centigrade for water. And this is the unknown, right? We want to find out what the mass of the water is. So the final temperature for water is 24.2. And the initial is 22.3 degrees centigrade. Now, I'm sorry.
Sorry.
Go ahead.
What do we need to convert the grams and the specific heat to moles? Since we did it with the other one?
No, because we're looking for the mass of water.
Okay.
Right.
So we
And
just had to do it with aluminum since we're doing this with H2O. Okay, that's different.
right, because
We're keeping
this is in grams and this is in moles. But this whole term right here is joules.
Mhm.
And this whole term is also joules.
Okay.
So let's resolve this one. 24.03 and then 1.205 times and then 24.2 and 82.4 minus and then times that. I messed up. 1.205. Okay. 24.2, 82. Okay, so this one is negative because of that. 1685 joules. 1,600 joules. And then this one is, what's the difference there? 24.2 and 22.3. That's 1.9 degrees times 4.18. This is 7.942 times the mass. Okay? Now, we need to, before this, since this is that times that, this has to be moved over here. So it's a negative there, it'd be a positive on this side. Times the mass of water. So now if we divide both sides by 7.942, right? That puts this one over here and gives us our answer. So let's see, I still got it in here. Yeah, there it is. Just need to change the sign because now it's positive. And 7.942. So I get 212. Yeah, three significant figures. 212. No, that's not right. Grams. 212 grams of water. Okay. That's a lot of numbers up there. So you have to be methodical at every step and stay focused on the controlling formula. Here. Well, actually, this one first. That establishes the relationship of everything in the calorimetry. Then each one of those is represented by its individual calculation. Okay. Now, we'll go to the calorimeter constant. Is there already a problem in here with calorimeter constant? Or is that with the lab? Does the lab have one in the first page? Yes. Oh no, that's clarification. I'm sorry. Here we go. Thank you. And I'm going to have to, so that I wouldn't have to make something up. Maybe I can do it theoretically. Be cold? Oh, okay. I can't tell because I wear a lab coat all the time. So let me remove this. Okay, so that was theoretical where the calorimeter didn't count. But the calorimeter that we're going to use is a construction of styrofoam cups to isolate the system from its surroundings, which it does very effectively. But the problem is the calorimeter has a heat capacity of its own. So if the reaction you're studying gets cold, then it's going to draw heat from the calorimeter. If your reaction gets hot, then it's going to dump some of that heat into the calorimeter. And we need to account for that. You know, how much is it? Well, our calorimeter is constructed from styrofoam cup and a plastic lid and a metal loop for a stirrer and a thermometer. And each one of those has its own individual heat capacity. So we can't keep track of all of them. So what we do is we combine. So if we had the Q that's associated with the calorimeter would, if we could, have that expression, but we don't know what that is, right? Because the thermometers would be different. I mean, they're not that uniform. Then a different wire, and then a different cup. So what we have to do is we combine that term into a C, our calorimeter constant. Okay? So if the S is going to have units of joules per gram degree centigrade, and this is grams, and that cancels that out, and the units here are simply joules per degree centigrade for the calorimeter constant. Okay, so now how do we deal with that in the lab setting? All right. Oh, by the way, this is one caveat. Once you construct your calorimeter with all those components, don't change any of them. Because if you change one, you change that. Right? If something happens, you break your thermometer, you got to start all over again. Okay? Or if you poke a hole in your cup and you have to get another one, start all over again.
Be very careful.
Okay, so the same type of, the same principle is operative for our calorimeter as it was for that theoretical. Only now, everything has 0, and we have, well, let's see, first one is acid-base neutralization reaction, isn't it? Yeah, neutralization. Okay, so we're going to have a Q that's associated with the acid, and a Q that's associated with the base, and a Q for our calorimeter. Okay? Okay, so each one of these is going to have its own, like that, and this is just going to be the C times the delta T, the calorimeter constant times the T. Oh, I'm sorry. What am I thinking of? Are you writing in pencil or pen? You have to just be crossing out. We're trying to calculate what the calorimeter constant is. Right? We don't do this experiment until we know what C is. Okay, so how do we do that? All right, we boil water, and we use room temperature water, and this is all distilled, distilled water. So this one's going to be the Q for the hot water. This one's going to be the Q for the cold water, or room temperature, and this is going to be the Q for the calorimeter. Okay, so the Q for the hot water. And since we're using water for both of them, they have the same S, right? And we choose to have the same mass. It just simplifies everything, right? And I think it's 50 grams for each one. Okay. how do you measure water in grams? Well, you could, but it's simpler just to assume that water has a density of 1 gram per mil. You're going to measure out 50 mils. That means you have 50 grams.
50 or 75?
Oh, 75?
So then put on number 7 on procedures.
Wait a minute.
Oh. Okay, that's fine.
We use a 100 mil graduated cylinder, won't we?
Yeah. Okay, we'll have 75 here. You know, that's even better. Because a larger mass, if you have the same percentage error, then a larger mass will give you a smaller absolute error. Right? So large mass is a good idea. 75. And the cups will hold it. They'll probably hold 300 mils tops. So you've got plenty of room. And of course, this is going to be 4.18. And then the change in temperature will be something else. Okay, so for the change in temperature for the hot, well, let's do it down here. So delta T is going to be final temperature minus initial temperature, and this one's going to be final temperature minus initial temperature, and this one's going to be final temperature minus initial temperature. Okay. The final temperature for every one of these is the same. Same as that one, same as that one, same as that one. Because they're going to equilibrate before we measure that last temperature. So the final temperature is going to be the same for every one. It's the initial temperature that changes. Where do you start from? Well, for the hot temperature, you'll be like maybe 60 or 70 degrees. And the water's going to be boiling when you start. But why is it going to be 70 degrees or less than 100? Well, you want to be able to measure the temperature right before you put them together. So what you do is you boil your water, then you measure out 75 mils in your graduated cylinder. It's going to heat up the cylinder and lose some temperature. And you pour it into a separate styrofoam cup, sit it over here. Put a thermometer in it. That's going to absorb some heat too. Then, in the cold, you take 75 mils measured of room temperature distilled water, right? And pour it into the calorimeter, okay? And let it equilibrate, because the calorimeter is going to absorb some of the heat too, or give up some heat, whichever the case may be. But then you measure the temperature of the water in your calorimeter and watch it until it settles, so it stops moving. Okay, that's the initial temperature for the cold. That's the initial temperature for this one and for that one, because they're together. Okay? Right, so you've actually got 3 temperatures. The final temperature is the same for everybody. The initial temperature for cold and calorimeter are the same, because you put them together and let them settle first. Then, the initial temperature for the hot. So you're going to have 3 temperatures. Now, the temperature you read on the hot is an instant before you combine them. You check the temperature, then you pull your thermometer out and try to leave as much behind as possible. And then dump them together. Close your calorimeter and mix it. And then you watch the temperature. Where does it settle? Well, it's going to start low and end up high. Right? Because this is going to be the cold side, and it's going to absorb some heat from this. Once you find out what that final temperature is, then you've got these terms locked in. You've got the constants locked. You got all these 2 constants locked in. You've got these masses locked in. This is the only thing that's unknown. Solve for it. And that'll give you your calorimeter constant. in terms of joules per degree C. Okay? So once you find that, then you guard your calorimeter from destruction and save that value along with it, and then proceed to the experimental part. Okay? And this will give you practice in working with your calorimeter too. So when you actually do the experiments, you'll know how the thing functions and you'll be able to work it better. Usually, if some methods call for just jumping into the experiment, and they say, assume calorimeter constant is this number. Usually they assume the number is about 10. So it's not really big, but it's significant enough to skew your values a little bit. And it's a good exercise. Because you're just working with hot and cold water. You know, no chemicals involved. I mean, water's a chemical, but nothing hazardous. Okay? So then the first one is going to be acid-base neutralization. And just remember the concept. You want to be able to measure the temperatures right before you put things together. Right? If you were working with, say, what's the first one? Sodium hydrogen carbonate? I mean the second one, sodium hydrogen carbonate. Sodium carbonate, okay. So the sodium carbonate, you're going to measure out a certain mass, put it in solution, and you've got the operative here. You're going to have the Q of the reaction, right? You have to assume that the sodium carbonate that you add to that solution doesn't have its own specific heat capacity. It's only the water that's in there that you're concerned with. So you have the water in there first, measure the temperature, and then you put this in, measure the temperature after. And that gives you the Q of the reaction. And then your calorimeter, of course, you have to do that one. So the initial temperature for this one is going to be the same as the initial temperature for that one, because the water's in there first, and they settled. So you've got initial temperature here. And then the final temperature is going to be whatever it changes to, and that's the same for both of them. So you're going to have a Q for the reaction, right? So that's so many joules of heat. And then that heat is going to be related to how much sodium carbonate you put in there. So I'm not sure. Do they want you to report it in joules per mole? Probably joules per mole. Laboratory questions. Enthalpy of solution. Well, let me see. Did I give you a table to compare it with? Yeah, here it is on the back page. It's per mole. Okay. So you're going to have to take the mass here and convert it to moles so that you can calculate joules per mole. And once you have joules per mole, you can compare it to the value that's given at the back of your table. See how close you are to it. Actually, that report, the value there is in kilojoules per mole, isn't it? Okay. So you got to be sure that your units agree. Okay. So that's heat of solution for sodium carbonate, and then you do another one for sodium bicarbonate. Okay. One of them is going to be exothermic, one of them is going to be endothermic. Okay. The heat of, I'll let this one till last. The heat of neutralization is actually the first one you can do. So you have Q for your acid, Q for the base, and then Q for the calorimetry. You know, if we have if we start off at the same temperature, we can combine these. Right, the method does tell you to start off at the same temperature for both of them, doesn't it? Until they come to the same temperature. In other words, they're sitting in the room, and you're measuring the temperature, and you want them to, whatever they start at, separately, to equilibrate at the same temperature. And if they start at the same temperature, then the final temperature will be the same, and you can combine that into the one term. Right? So you have you can have a final temperature minus an initial temperature. And if the initial temperature is the same for both of them, then the final temperature will be the same, and that's your delta T. So what's the mass? Well, the mass is the combination of both of them. I think you have 60 mils for one and 50 mils for the other, I think. I don't remember which one it is. So that would be 110 grams. And then we assume the specific heat is the same as for water, because these are relatively dilute solutions. And the presence of acid and base isn't going to change the 4.18 joules per gram degree centigrade. So in that case, what you end up with is this as hold on a second. Okay. Okay, I skipped a step. This is fairly standard stuff. The heat of the reaction plus the heat of the calorimeter. Okay, so we know what this is, because it's going to be our constant times the change in temperature. And we measure the temperature before and after. Why am I getting confused? Let me see that other paper.
That's why I did this, so I can look at it and not be confused too.
Okay. We're separating terms. Okay. Let's start over again. So Q associated with the reaction itself is going to have an influence on Q of the water. And then we have Q of the calorimeter. Okay. So how much water do we have in that vessel when we add the acids and bases together? 110 grams. Right. And we also have 4.18 as our S value. And we have the initial temperature, final temperature minus the initial temperature. Okay. So that's our Q for the water. That's a known value. This one's a known value because we have C times the delta T. This is the unknown value. What's the heat of the reaction? Okay, so once we calculate this one and this one, we just put those on this side. That's equal to the heat of reaction. Excuse me. So now once you know the heat of the reaction equals so many joules, then how do we express that in terms of, how do we express that in terms that we can compare to a known value? Right? We know the total number of joules, but where are the moles? Right? So you have your acid-base neutralization. You've got sulfuric acid plus sodium hydroxide, I think. Yields what? Sodium sulfate plus water. Okay? So this is going to be 2. This is going to be 2. There we go. So typically what you do is you express this heat in terms of how much water is produced, because it's an acid-base reaction and water is always an end product. This will vary, depending on the acid and base. So you can't express it in terms of that or in terms of these because they're different. But this one is always the same in every acid-base reaction. So we need to find out how many moles of water were produced in that reaction. Okay? So how do you do that? Which one is the 60 mils and which one's the 50? Actually, which one's the 50? Right, one of them is in excess. Let me see. Yeah. Okay, measure 50 mils of sodium hydroxide, 60 mils of sulfuric. So sodium hydroxide is the limiting reagent. 50 mils. 50 milliliters of 1 molar sodium hydroxide. So why do we say 60 mils of half molar sulfuric acid? Because we want the reaction to go to completion, right? If we try to match them up and say, all right, 50 and 50, well, this one might be 51 actually, and this one might be 49. So the reaction won't go to completion. We want to know which one is in excess. This one's in excess. This one's the limiting, so everything is based on this one. Remember our limiting reaction spiel. So how many moles is this? Well, that's 0.05 liters. So 1 times that is 0.05 moles of sodium hydroxide. Right? This one is actually, well, half molar sulfuric acid is actually how much acid, how many protons. It's twice that. Right? So that would be 0.060 moles of protons, and this would be hydroxyls. Right? So this is the limiting one. It's going to run out. But this is the one we base our calculations on. So what's the ratio? Well, 2 to 2, right? So we produce exactly the same amount of water, 0.050 moles of water. Okay? So now, once we know how much heat is evolved in this reaction, and it will be exothermic. It'll be a negative value. So whatever the negative x is, we divide it by the number of moles of water, and we have joules per mole of water produced. Negative joules per per mole of water produced. And if you look at that last page, where you have the table of accepted values, there it is. That last one down there, minus 57.9 kilojoules per mole. That's the accepted value for an acid-base reaction. Kilojoules per mole of water. So you should expect this value to get in the neighborhood of minus 57 kilojoules per mole. Okay? Did I lose you? I almost lost myself. Because I only do this once a semester, and it kind of fades. Okay, so this is standard stuff. You have Q for the reaction, and then you're actually measuring the heat in terms of water and the calorimeter. That's how you find out what the Q for the reaction is. Okay? 2:15, how are we doing on time?
Okay. We can go to 3:30 if we have to.
All right. So that's an explanation of the lab we're going to do today. Okay.
Now we can go back to these problems, however you want to do them. Ooh, it looks interesting. That's going to be pretty involved. Let's see if we can find one that's a little easier to deal with. Well, my brain's getting blurry. Let me go to the back and work myself forward. Usually the harder ones are at the end. Oh, heats of reaction. Hess's law? Yeah, we haven't got to that yet. Ooh, we need to do some of those. Okay. I see a bunch of them. Let's see. Start with, I don't want to get too complicated right at the beginning. Okay, those are A, B's, and C's. I don't like those anyway. I don't know why I put them in there. What if we try It's 59, like. Let's try 59. So if we're given enthalpies for these 4 reactions in the box, the question is, can we calculate the standard enthalpy for the reaction given below, P4O10 plus PCl5 yields Cl3PO? And the answer is yes, we can. It just takes some work. So 59. So let's put the target equation up here first. And whoever designed this problem was kind enough to balance the equation for us. Okay. So we have these equations, and you may not necessarily need all 4 of them. So what you do is you look at the components here and find the equations that have those in them. So let's look at the first one. There's a P4 plus 6Cl2 and PCl3. Okay, that one doesn't fit yet. That doesn't mean we don't need it, but this doesn't say we need it. So let's move to the next one and see how about it. That one has P4O10. Okay, so number 2 will function for this one. P4 5O2 yields P4O10, and then the delta H is equal to minus 2967.3 kilojoules. Okay? Now, what's wrong with that equation? It's backwards. Right? We need the P410 over here on this side. Okay? So why don't we just do that? So let's flip it. And what does that do to delta H? It just changes the sign. Okay? So we're going to use this one. I use asterisk because this one gets pretty messy. So the one that I'm going to use is the one I put an asterisk next to. So we got this one covered. Do we have a PCl5 in there? Let's see, number 3. Yep, there's a PCl5, number 3. So that's PCl3 plus Cl2 yields PCl5. And the delta H for that one is minus 84.2 kilojoules. Okay. So that one's on the wrong side also. In addition, there's not enough of them, right? So what we have to do is flip it and multiply it by a constant, right? So we've got to multiply the whole thing through by 6, plus we have to flip it. So if we do that, we have 6 times this one, and that's good because that gives us this one, yields 6 of these, PCl3, and 6 of these, Cl2. Now what does that do for this one?
Well, it changes the sign, and we multiply it by 6. So minus 84.2, well, 84.2, because we changed the sign. So that's 505.2. 0.2 kilojoules. Okay, so now we got this one that we're going to use. We got those two terms covered. Now we need Cl3PO.
And we got one of those in here.
There it is. Cl3PO is number 4. So that's PCl3 plus 1/2 O2. I'm leaving out the solids gases in there. It just takes up too much room. Cl3PO. Okay? And that delta H is minus 285.7 kilojoules. So what's wrong with this one? Well, it's on the right side, just not enough of them. Right? So we need to multiply what? 10? And I always put brackets around everything, even the delta H, because that reminds me I need to multiply 10 times the delta also. Okay, so now we got 10 PCl3 plus, what's 10 times 1/2? That was a trick question. Cl3PO, and then 10 times this one, which would be, still minus, because we didn't flip this one, 2857 kilojoules. Okay? We're going to use that one. So that covers this. Are we done? No, because we've introduced another compound, PCl3, which is not up here. It's not in this one, but it is in this one, and it's in this one. Well, as is, this PCl3, 6 of those cancel 10 of those and leaves 4. Right? So what we need to do is we need an equation with 4 PCl3s on this side to finally get rid of those. So that means we've got to go back to number 1. That's where our PCl3 is. And as written, there are 4 PCl3s there. So we can write that one in as is, and that's the one we use. So this one has P4 plus 6Cl2, and then 4 PCl3s. Yep. And the delta H for that one is minus 1225.6 kilojoules. Okay, and we're going to use this one. Now, if we can do this without getting cross-eyed, because I don't have enough board space to bring them all down and then cancel. So we're going to have to cancel as they're sitting here. So when we, let's see, let me mark these also. Okay. So we've got, that's good. These terms are all fine. We've been doing those as we go. We've got to look for the oddballs, right? Because this one is good, but we've got a P4 and a 5O2. There's the 5O2, right? On this side and on that side. And let's see, they're part of the asterisk? Yes. So we're going to take those out right there. How about P4? Because P4 is not in that one, because we have a P4 down here. Here's a P4, just one of them. Right there and right there. Okay? So that leaves this one with only that term. So this one's good. How about this one? PCl5. Okay, there's 6 PCl5. It's good. 6 PCl3. And 10 gives us 4. And there's the other 4. So there's 4 here on that side, 6 on that side, 10 on this side, 10 on this side. All of those are gone. Okay? So that leaves chlorine, 6 chlorine. Here we go. 6 chlorine on this side of the arrow, 6 chlorine on that side of the arrow. So those 2 are gone. This one's good. This one leaves us with that term. That one's good. This one's gone, that one's gone, that one's gone. Okay, we're good. We canceled everything that we don't need. That means that when we add them together, they will give us that formula. And you can check yourself, right? There's one. There's the other one. Those are gone. This one, this term right here, and there's nothing left of this one. That doesn't mean that you throw away the heat. You still have to add the heat. Right? So now we just add this one, this one, this one, and this one together. So we got 2967.3 and 505.2 plus, and then 2857 minus, and 1225.6 minus. So if I did my math correctly, delta H for the overall reaction is minus 610 kilojoules.
Yeah, let's see if I came out right.
Yep, close enough. I'm off by 0.1. That's because I didn't keep it. I should have kept it. Okay? That's a lot of work, but it's easier than having to conduct this experiment in the lab. And then 610 kilojoules is a lot of heat. So if you're actually going to do that one in the lab, it's nice to know that it's going to generate a lot of heat, so you need to take precautions. Maybe use small amounts, under protection, with lots of PPE, you know, and then you'll be safe. I've never heard of that compound before. Okay. This would take quite a while to do that one. So that looks like a bonus candidate. I would probably, if I had one in the required section, it probably wouldn't take 4 equations to do it. It might just take 2. You can do it relatively quickly.
Like 60. Okay, let's see. Sometimes I can find what I'm looking for better if I look at the answer. What am I looking for? Oh,
let's just review this part. How do we, what's the definition of standard heat of formation. Right, you remember that? Delta H, standard conditions, formation. Okay, that's the amount of heat that is either released or absorbed in the process of making a compound out of its elements. Right? So if you say, all right, what's the delta H for the formation of water? How about that one? Okay. This is where you start, and the product has to be 1 mole, always. So that's it, and you can't change it.
Can you say what that means again?
Oh, the standard enthalpy, that 0 means standard conditions. So 1 atmosphere, 25 degrees centigrade. If any solutions are involved, they're 1 molar. Okay. So the standard heat of formation, and the F means formation. That's my F. It's actually derived from calculus integral sign. I just found it easier to write that than to go in there and do. I don't even remember. I can't even write F anymore, except that way. What is it called? How do you write F?
With your cursor?
Yeah. I can't do it. I've been writing that way so long, I can't remember how. Yeah. They don't even teach cursive anymore, do they?
I've heard some schools.
That's stupid. They didn't teach it to my son. The only cursive he knows is how to write his name. He did learn that. He had, what do you call it when the teacher comes to your house? Not homeschooling.
Or in-house tutor or something.
Homebound. He was homebound. And the teacher would come to school. He has a form of autism also. He couldn't handle real school. Anyway, that's another story. So, in order to satisfy the conditions for the heat of formation, you need 1 mole of your compound. And then, whatever elements you have over there have to be over here. Right? Those have to be in standard conditions too. So under those standard conditions, oxygen is diatomic and hydrogen is diatomic. Right? Remember your diatomics. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. They're all diatomic under standard conditions. So they're diatomic. Now you balance the equation, if necessary, with fractions, because that one has to be 1. So we need half of an oxygen, right? That's just 1 oxygen. And we need 2 hydrogens. That's good. Oh, and standard conditions would be gas, and liquid. Okay? So that's how you write a standard, the reaction associated with standard heats of formation. Now, what can we do with that? Well, since it's written that way, then this heat of formation is associated only with that side of the equation. If you determine, it's assumed actually that the heats of formation of elements are 0. So this value is associated only with that. So now, if you have a chemical reaction with compounds in it, then you can determine the standard heat, not of formation, but of the reaction, if you know the standard heats of formation for the products and the reactants. And what you have to do is you sum up, that's what sigma means. You sum up the heats of formation for the products, and you subtract the sum of all the heats of formation of the reactants. Okay? Of course, recognize that this is in terms of 1 mole of that compound. So if your balanced equation has 2, 3, 4 moles, you have to multiply that times the standard heat for each one of the compounds. So that's why we stick this N in here. That's the number of moles associated with each one of these. Right? So you do this for one compound, and if you have 2 products that are both compounds, then you have to do it for the other one and add them together. And then for the reactants, do the same thing. If you have 2, 3, 4 compounds, it's how many moles of that compound times its standard heat. Then you add it together with how many moles of the next one times its standard heat, and you get that term and subtract it from this one. And that gives you the standard enthalpy for the balanced equation. Okay? I don't know, do we have one of those in here? We gotta have one in here.
Is 64 61?
No. We need Hmm.
67?
The heat combustion of acetylene, temperature, delta H formation. Delta H for acetylene. Yeah. It's not straightforward like this, but it uses that concept. And that's fine. Let's see, how did I do that one? I added those things up. How did I do that? Okay. Okay. The way I answered that question in here with the work problems, I used Hess's law. But I wonder if I can do it with this method. Let me see. Maybe we can. What are we doing? Okay, we're about to run out of time. So that was 67. Okay, the heat of combustion of acetylene is a value. So we have to write the combustion equation for acetylene. Right. So here's acetylene. And a combustion requires what? Oxygen. That gives up heat. So the products are going to be carbon dioxide and water. So we have to balance the equation. Let me see if I can do this without dragging it all out. Let's see, 2 carbons. Okay, that gives us 5 oxygens, 2 hydrogens. Oh, okay. So we got the 2 hydrogens. We got 5 oxygens. So I need 5 halves there. That means multiply the whole thing through by 2. There we go. Now let's see if that worked. 4 carbons, 4 carbons. 4 hydrogens, 4 hydrogens. And 5 times 2 is 10 oxygens. So it's 8, 9, 10 oxygens. Okay, we're balanced. Now, the other bits of information we're given is standard heat formation for CO2.
So CO2, and we have carbon, standard conditions, and oxygen, standard conditions. So 1, 2, that's it.
And the heat for that standard,
The standard heats of formation for that one is minus 393. What are the units? Kilojoules per mole. Okay, CO2, water. So we got water, we wrote that one in before. Yeah. So this is going to be oxygen, hydrogen, there. We need half an oxygen. And this one is going to be minus 286 kilojoules. Now it's okay to say kilojoules per mole for these because it's in terms of the product. It's always 1 mole. Right? When you see the delta H for any reaction, it's in terms of the whole balanced equation. That's it. So if you have 1 mole of something here, it can be in terms of that mole. But if you have 2 here, then it's half that per mole of that product. It depends on what you need. But for our terms here, this is accurate. This is that many kilojoules per mole of that, per mole of this. Let's see. And we're also given this one at minus 1229 kilojoules. Okay. This temperature, calculate the delta H for a formation for acetylene. So the question is, what's this one? So we have carbon, hydrogen. So we need 2 of these and 1 of those. Gas, solid. So the question is, what's this one? Okay. So if we want to match up these to that one, you can use Hess's law, but let's see if we can use that formula, right? So the heat of that reaction is minus 1229, minus 1229 kilojoules for that reaction. Now, what is the standard heats for the products? Well, there's water, but we need 2 of them. Minus 286, right? So that takes care of water. There's CO2, we need 4 of those. Minus 2, 1, 2, 2. Oh no, wrong one, sorry. CO2, here, minus 393. Okay, so that's the products. Okay, now how about the reactants? Well, the reactants, we've only got 1 because remember, elements don't have a standard heat of formation. They're 0. So we just need to know this one 2 times this one. That's our unknown. Okay? So now we have an equation in 1 unknown, we can solve it. Can't we? Theoretically, we can solve this problem. So let's resolve this term right here. So 2 times minus 286. And then 4 times minus 393. Okay. that's minus 2144. Okay. For that one. So if we take that one, change, of course, when it comes across, change the sign to positive, and then 1229, then this side of the equation becomes 915 kilojoules equals, wait a minute, it's still minus, right?
Yes. That's what.
No, I'm sorry. Because that's positive. And this is bigger than that one. So this positive eats up all that and leaves us that many positives. Right? This becomes positive on that side. It's 2,000, that's 1,000, so this is reasonable. So that's plus. And we're left on this side with minus 2 times delta H formation there. So delta H of formation for acetylene, C2H2, is equal to this one divided by minus 2. Or 458. Yeah, 458 minus kilojoules. Now,
Is that the answer? 67. No, it's not. So why is it not the right answer? I did something wrong. I don't know what it is. It should have worked.
It's double what the answer should be.
Ah,
Difference.
okay. So,
Well, in negative.
yeah. Let's hope I don't give this one to you on the test. Did I do something wrong? Let's see. We were given the heat for this one, minus 1229. There it is. Heat of combustion of acetylene. Okay. This is per 2 moles of acetylene. So this value needs to be divided by 2. Then, yeah, that's per 2 moles. So if we do that, what happens? Okay, we're running out of time. 1229 enter 2, so that's 614.5. 614.5. Then this is positive, negative here. Did I do that right? That's negative. That's negative. Negative. Becomes positive on this side. Ah. So I get 1529.5. Positive. That still gives me a negative value. That also gives me 4 times as much as I need. 765. So I just went from bad to worse. Okay. So I haven't figured that one out yet. If we use Hess's law, we get that answer. If we use this one, it just gives us an answer. So I can't say which one's correct. Hess's law should work. And the only thing that I can say in that respect is I worked it out with Hess's law and I got the answer that the authors gave me. So they're saying that Hess's law is the way to go. So let's look at, wait a minute, the standard heat of formation. If we're going to combine carbon and hydrogen together to make acetylene, and acetylene is extremely exothermic when it reacts with oxygen, then it's as if we have stored energy in that molecule. That means it's endothermic to create acetylene. So the value should be positive, not negative. I'm going to have to work on this one, because theoretically it should work. I just can't figure out what I did wrong. Okay. So time to go in there and do our thing. Oh, wait a minute. 3:45. 3:45. Oh, we got more time. Are there any problems that I didn't cover that we need to do? Let's see. Otherwise, we ought to go in there and get done before the sun goes down. Let's see. How about these at the end? This fossil fuel was formed from the remains of plants that were buried and exposed to high pressure and heat over time. West Virginia's favorite, coal, yeah, coal. The coal with the highest energy available per unit burned is which? Do you know the different types of coal? Okay, the highest energy content coal is anthracite. Presumably because it is the highest organic density. It has the least ash. The next one is bituminous, which has a little more ash. Then subbituminous, and then lignite is muddy coal. It doesn't even look black. It's more kind of a reddish orange color, lignite. You still get energy from it, it's just not efficient. Let's see, which of the following is both a greenhouse gas and a fuel? Well, carbon dioxide can't be a fuel. Coal's not a gas. Freon doesn't burn. Nitrogen doesn't burn. It's got to be methane. Methane is a greenhouse gas. In fact, methane is, what, 4 or 5 times as efficient as CO2 at trapping infrared radiation. That's why, what was that woman's name? The color, I was trying to think of her abbreviation. AOC. You know, from Brooklyn. That young woman that's tried to push the Green New Deal on us.
Oh.
She published the Green New Deal and then took it down really quick because it was so stupid. But they wanted to stop cows from farting. Okay, never mind. What's one of the main advantages of hydrogen as a fuel is what? When you burn hydrogen, combust hydrogen with oxygen, what do you get? Water. Water. That's it. You know? Eventually, the EPA will get around to calling water a pollutant, too. They've been trying to do that to CO2 for years.
Congress won't let them do it. Courts won't let them do it either. Which one is not being considered as an energy source for the future? Ethanol, methanol, oh, they're okay. Seed oil, yeah. Shale oil, carbon dioxide. Okay. Here's the short version. The only thing that can be used as a fuel is one that is reduced. In other words, it can supply electrons in a redox reaction. Right. So, have we done oxidation states in here? Okay. The oxidation state on carbon, if we say oxygen is -2, then that's -4 total. So oxygen has to be a +4 oxidation state. Okay? Whereas methane, where hydrogen is +1, is +4 total, is -4. So which way are the electrons going to flow? They're going to go from this one to make that one, right? This one's going to be oxidized. It's going to lose its electrons to something else. Because that one's a 0 oxidation state, and we're going to produce CO2 and water. So this one is going to go from, well, actually the oxygen is going to stay. No, this is -2. Yeah, and this is +1. So this one's going to go from 0 to -2, right? So it's going to gain electrons. It's going to be reduced. This one's going to be oxidized. Oxidized. So you can't go backwards, right? You got to go this direction. So that one can't be a fuel because it has no electrons to supply, right? It's not going to give up electrons and go back that direction because giving up electrons goes this direction. That's why carbon dioxide can't be a fuel. So you need a reduced compound of some kind to serve as a fuel. That's why all the hydrocarbons are good for fuels, because the carbon in hydrocarbons is at least, well, not at least, at most -4. Sometimes they're less, but they're all reduced. And then you burn them and you go toward this one. That's probably why methane is a very efficient fuel, because this is the most reduced you can get, carbon, -4. I don't know about the others. I have to calculate them. Now I don't want to bore you with that. But that's the short version. That's the explanation why this one can't be a fuel, that one can be a fuel. Okay. Any other? Let's see. All right. We got some short answers in there. '87 uses Hess's law. 88 does too. 85. How much energy? Okay. I don't know what to tell you. You have to tell me if you're happy with where you are, or if we need to spend some more time on it. Because I'm all talked out.